The topic we have is called, and its next way of solving is if you have an exact equation, exact. Okay, so notation wise, you're going to get something that looks like this. So say it's like y x dy equals 0. Okay, now this is really just, if we go back to what's the derivative of x times y, you could see here I would get y plus dy dx x, right? And then if I rearrange some things, I could have it written as, say I multiply everything by dx. So I have y dx plus x dy, and then equals 0. You could have like that. But you could see that this is just your derivative here. Now, this is both linear, right? Linear like we just did, and it's separable. Okay, so we could go back to this example to show, again, another method of solving a type of differential. But sometimes you're going to want to use this method because it's easier to solve. So if you think about even this notation here, what you really have is, for the setup or the look of it, you have your partial of, say, some function f with respect to x dx, right, plus a partial with respect to y dy. And this is something that you would see in like Calc 3, right? And this was equal to dz. Okay, but if you notice, right, let's say that f of xy was equal to xy, right? You could see here that your partial of this with respect to x is y, and your partial of that with respect to y is x, and that's where we get this notation here. So that's all well and good, but I mean, again, you guys probably want to know, how to solve these things. All right, but just to go over this last notation, let's say you have, and this is what we're trying to do, is trying to get back to some solution that would look like this, right? It's kind of like from Calc 3 where you have a function of x and y equal to a constant, right? So when you're solving these, you could see why I'm going to start to use partials right here, because what's your partial with respect to x of this function would be 2x minus 5y, right? Our partial with respect to y of that same function is going to be negative 5x plus 3y squared, right? And then you could see how that notation fits in, where it's 2x minus 5 and then dx plus the negative 5x plus 3y squared dy, and then that's equal to 0 because the derivative of, right, a constant would be 0. Okay, and you can see that's how this type of notation would work. But the reason why I want to show you that is knowing our partials is a way to check and then work ourselves backwards to try to find a solution. Okay, again, just theory there, just some notation properties, so don't worry so much about that, because what you're going to want to see is, well, how do we tell that we have an exact equation? Okay, so an exact equation is going to look, you're going to have some function of xy times dx plus some function of xy times dy, and try to stay consistent with the lettering. So m, right, m is always with dx, n is always with dy, because it goes in alphabetical order. and then it's going to equal 0. Now, if the differential is exact, differential equation is exact, then two things, okay? Well, one thing, your partial with respect, partial of m with respect to y, so like the opposite, right? Is that equal to the partial of n with respect to x? So like, I'm just going to scroll up. Even if we go back here, right? Let's look at the y here and the x, right? So in this situation, my m, because it's first, is with the x. Not because it's first, sometimes they rearrange them. But here you get y, n is x, right? So what's my partial of m with respect to y? Well, that's going to be 1, and your partial of n, partial of n with respect to x is also 1. So that's why not only is this linear separable, it's also exact. Okay? Alright, so let's go a little further here. So this is number 1. This is to check, okay, to check if a differential is exact. Okay, you want to use that. Alright, so our first example that you're going to have is just to show that, right, show that 2x dx, 2xy dx plus x squared minus 1 dy equals 0 is in fact exact, right? Show that. So what I want to do is just show dm, not dm, partial of m with respect to y. In this situation you would get 2x. Is that equal to the partial of n with respect to x? And you could see that is, right? So we're looking at partial of this, right, with respect to y, and partial of this with respect to x. So does it work out? Sure it does. Okay? So it is exact, so we check, right? That is exact. Now, how do we solve? So I'm going to solve this one first, and then I'll go over the steps next to it so that you guys see what I'm doing, because it's a little tricky here, but again, if you get the idea of what I was saying about the partials, right? So if we go back up top, okay, you can see, where am I at? Right here, this notation here, right? So what I'll do is, let's cut that out. Okay, and really I don't want that part. And let's bring this thing down. Okay. So, do a little cleaning up. Okay, great. Okay, so now, and then equals equals 0. Okay, so if you're looking at this, right, and we're lining up what we started with, like 2xy dx. Okay, so that's your partial with respect, right? That's your partial with respect to x, okay? Plus the x squared minus 1 dy, and that's your partial of f with respect to y. So I want to work backwards, okay? So what I'm going to do is, you could start with either one. It doesn't matter if you start with the dx term or the dy term, it doesn't matter which one you start with. So the first thing I want to say, okay, how can I find what my original function is let's do an integral of one of those parts. So I just picked the first part because it's first, no specific reason. And remember what this means though, you're taking the antiderivative with respect to x. So it's like almost like a partial antiderivative, right? So really the only variable that I care about is the x in this situation. And what I would get is x squared y. Remember, y stays constant plus some type of constant. Now, I'm going to get rid of that because if you think about this, this was just a partial, right, with respect to x. So if you had a function of y added to it, it would go to 0 because it would just be a constant. So I'm going to get rid of this constant and I'm going to write g of y, some function of y since the derivative would be 0. With respect to x equals 0, right? Okay, so now this could also still be a constant because it doesn't matter. It could either be a constant or a function of y, which really, even if it's a constant, it's still a function of y in a sense, okay? So now you have this as your f of x, right? So what we want to do is take the derivative of what you found with respect to y, okay? So you're taking the derivative of what we just got, right, now with respect to y. Okay, remember you started with respect to x, now with respect to y. So this is going to give me x squared plus g prime of y, right? And what we want to do is set that equal, right? Because if you think about it, this is going to be your partial. Really, this is your partial with respect to y, right? Partial with respect to y. So we're going to set it equal to the partial with respect to y, which is up here. So we have x squared minus 1. Now, solve for, right, y g prime of y, which is just going to be 1, negative 1. Okay? All right. Now, so if you notice, we did an integral with respect to x, but we didn't do an integral with respect to y. So the last step to find what g of y is, okay, to find what g of y is what we were missing here, right, for our function, okay? I'm going to do an integral of g prime of y with respect to y. So here I'm going to have negative 1 dy, which gives me negative y plus, now it's a c because we already dealt with that first function of x, right, and we did our integral and got that out of the way in the beginning, because if we did that integral with respect to x, we would have had something with an x. Now you actually have that c value. And then our final step is just to put, right, your, I should write it this way, your g of y, okay, in for g of y for our final step. So you're going to get something that looks like this, x squared y plus or minus y plus c equals 0. Sometimes in WebAssign you might have to write it like this. Okay, it doesn't matter the way you write that, but I think either way you will get credit, and that is your solution to that exact equation. All right, so let's put steps down for you guys. Okay, steps. Okay, so the first step, right? Think about your problem in this form. You know, I know you have the mxy dx plus n xy dy equals 0, but maybe think of it as that's your partial of f with respect to x dx plus the partial of y with respect to y dy, and that's equal to 0. This way it kind of helps us. So when the first step is, you're going to have this function equal to the integral of whatever one. So if I'm picking x, I'm just going to go with that. If you could go the other way around, right? If you pick the y one, it's okay. Okay? So you're doing that integral of that partial with respect to x, okay? Okay, now with that, right, you'll have some function there, and you're going to want to then, basically what you're doing is finding out what is your differential with respect to y by taking the derivative of what you just got with respect to y. And just don't forget in this one, you'll have a g of y as c, okay? Once you get this derivative, right, 3, set number 2 equal to the partial of f with respect to y, which means that you're setting that equal to that portion of the function, the differential right there. You could think of it as, right, this is right here was our partial with respect to y. You're setting that equal and solving for, I'm going to say g prime of y. Okay, and then your final step is to find g of y. Is you're going to take number 3 right here, so you're going to take the integral of g prime of y with respect to y, and then finally substitute sub number 4 into number 1 for g of y. Okay, now I know this is a lot of steps here, so I'm going to do a couple more examples with you guys, but I don't know if you can just use those steps accordingly, right? So really it's going to be all of that are your steps, okay? This might be confusing, but maybe as we go along it makes a little more sense as I continue to do more and more examples. All right, so I'm going to scroll up and let's get going on some examples here. Okay, so let's do another one. Example 2. Right, so here we're going to have e to the 2y minus y cosine xy Okay, so the first thing I want to do is check to see that it is exact, right? Check to, I'm just going to check for exact. All right, so your partial, right, of m with respect to x, man. Sorry about that. This is dx. So, and I messed that all up. This is dx, and your partial of m with respect to y. Sorry. So here you're going to have 2e to the 2y, okay? And derivative of cosine is negative, so it's plus. And then chain rule, so you got to think, what is your derivative of the inside xy with respect to y would just be x. So it's plus xy sine xy. right? Now, is that the same for your partial of n with respect to x? So here, you get 2, right now I'm working with this, 2 e to the 2y minus, same idea here, which is going to turn into a positive, and you're doing that same partial with respect to x now, which is just going to be y. So it's still xy sine xy. So this does check. Okay, so let's go through the steps. So the first step I'm going to have is my function, or my solution that I'm looking for, is going to be the integral of one of these portions. I kind of always use the dx side, but again, whatever one you feel is easier, go right ahead. Okay, so this is with respect to x. So what I'll do is, okay, with respect to x, I'm going to get x, because anything with a y is just constant. And now this is tricky. So antiderivative of cosine is sine. So you'll know you'll have a sine xy inside there. But what do you do if you had, like, what is the anti of sine 3x, right? You know that's going to be negative 1/3, so you get that negative 1/3 to come out. Okay, so in this situation, all right, we'll have y divided by y, right, which is nice, and then plus g of y. Okay, remember that's really like a constant there, but we don't know what our f function would be yet. Okay, so here let's just clean this up. So we have our function, right, where we canceled out those y's, and now let's take the derivative of that with respect to y, right? So I'm taking the derivative with respect to y of what we got in number 1. So with respect to y, I'm going to get 2x e to the 2y minus x cosine xy, right? Remember that's chain rule, right? So with respect to y, and then plus g prime of y. Okay. Third step, all right, we're going to set what we got equal to what we didn't use yet. Okay, what that second portion of our equation, that second term, all right, which in this one was the 2x e to the 2y minus x cosine xy, and then plus 2y, all right? And once we do that, then we're just solving for that g prime of y, which in this case, we would just get 2y, which is nice. And then the last step here is to find what g of y equals. We take the integral of g prime of y dy, which here would be y squared plus c. Okay, now we could plug back in, right, our g of y in for g of y. So I would get, my final solution would be x e to the 2y minus sine xy, and now plug in, so I'll plus y squared plus c equals 0. And there we go. All right, let's do an IVP in their initial value problem. Okay, what example are we on? What was that last one? Example 2. Okay, so here's example 3. All right, so here you have dy dx equals x y squared minus cosine x sine x over y 1 minus x squared. Okay, so let's rearrange it so it's in the form that we like, right? Also, there's our initial value. So, right, if you're cross multiplying and bringing everything over, right, you're going to have like y 1 minus x squared dy. Here we'll have x y squared minus cosine x sine x, and then dx, right? But let's bring that to the other side so we can, I'm just going to change signs here because we're bringing it to the other side. So that's a positive cosine x sine x minus x y squared dx plus y, and I'll distribute this y and then y x squared dy. Okay. All right, so let's show that it's exact first. Okay, is it exact? So we're taking the partial of m with respect to y. Okay, so that's 0, the first term, because they're all x's. Second term will be negative 2xy. Nice. And let's take the partial of n with respect to x. First term is 0 because it's y. Second term would be negative 2yx, which is the same thing. Okay. All right, so we know it's exact. Let's start with that first function here. Actually, you know what? Let's start with the second one because it's a little bit easier and we don't have to deal with the trig right away. Okay. And also, I just want to pick the other one to start with. So you have y minus x squared y, right, dy, and we're doing anti with now respect to y. So I'm going to get 1/2 y squared minus 1/2 x squared y squared plus, now it's a g of x because we used y first. Okay, so notice the difference, y, and it could be a function of x. So second step, right, just like I did before, you're going to take the derivative of now the opposite of what you did in the first one. So derivative with respect to x of our function that we had in number 1. Right, so our derivative with respect to x, the first term would be 0, second term would be negative x y squared plus g prime of x. Okay, now 3, set that equal to what we didn't use yet. Okay, so that first term we didn't use. So negative xy squared plus g prime of x is equal to cosine x sine x minus xy squared. So you could see that g prime of x is equal to cosine x sine x. Cool. All right, last step here. All right, let's find g of y, which is going to equal the anti of cosine x sine x, right, dx. So u sub, right, u sub, let's pick cosine x, du is negative sine x dx, right, so really that negative du, right, is going to be sine x dx. So just going over u sub, now I'm going to replace everything, right, bring that negative outside. You could see sine x dx was just du with the negative outside, and cosine was u. Very easy. Antiderivative is negative u squared over 2 plus c, so we'll get negative 1/2 cosine squared x plus c as our g of y. I'm sorry, g of x. Sorry. Okay, so we will then just plug back in, right, our g of x. So we wind up getting we get 1/2 y squared minus 1/2 x squared y squared minus our g of x, which is 1/2 cosine squared x plus c, all equal to 0. Now, this was an initial value problem, so I know it's a little lengthy, but let's go back up. What was our initial value? Was y of 0 is 2. So, let's see. So, if y of 0 equals 2, we're going to have plug in for y2, so you get 2 minus 0 minus, let's see, minus 1/2, right? Cosine 0 is 1 minus 1/2 plus c equals 0. So here I'll get 3/2 plus c equals 0. C is going to be negative 3 over 2. And then we could plug that back in, and we have that initial value function. So it's 1/2 y squared minus 1/2 x squared y squared minus 1/2 cosine squared x minus 3/2 equals 0. This would be a fine solution. They should accept it on WebAssign, but if we want to clean it up, we could multiply everything by 2. And bring that constant over, and then you have that as your solution to that original differential. But again, I know that this is lengthy, but you could go through the steps and, you know, try this over and over again on your own. And then when you get to the homework, really just repeat doing these steps. You should be okay with the repetitive stuff. Okay? The last thing I want to go over is how do you make a non-exact exact. A non-exact differential equation exact. Okay? So two things that you want to have. There's integrating factors, just like when we use linear, we had that integrating factor. So for exact equations, you want to use these, where we still have the same notation. Mu of x is going to be e raised to that integral of the partial of m with respect to y minus the partial of n with respect to x over n, and this would be a dx. Okay, or so there's going to be two of them, but you pick the one that's easier. Okay, or you have same idea. Mu of y is equal to e raised to the integral of partial of n with respect to x minus partial of m with respect to y over m, and then this is dy. Okay, so using these, so again, because it's an integrating factor, you're going to use this to make it non-exact, so we have to figure out which one to use and then multiply that through. So let's start with an example that I have here, which is going to be xy dx plus 2x squared plus 3y squared minus 20 dy. Okay, so it'll look like that equals 0. And we could see exact or not, right? So exact or not, let's try this, right? What is your partial of m with respect to y? Would just be x, but your partial of n with respect to x is 4x. Okay, so just going over a couple things. What I would do is focus on this first, because look, it's pretty sloppy if that's your exponent. So let's look at the first one, right? Let's do like, what would my m of y minus n of x over n equal, right? So here, if you did that, right, my m with respect to y would just be x, right? And then minus, right, 4x, right, your partial of n with respect to x, which is really just like checking for exactness, over n. But if you write this over n, this is a mess. So we don't want to use this one. Even though you simplify the top, you get negative 3x, but you can't simplify this any further. And who wants to do an integral of that function there? right? So I don't want to use this one. I'm hoping that the next one is a lot simpler. Okay, so here's 4x minus x over xy, and you can see this is much nicer because here we will just get 3 over y, which is very nice to use. Okay, so let's go to, let's go to what we're going to use. We're going to do that integrating factor that we like better. So this is with respect to y. So it's mu of y equals e raised to the 3 over y dy, and then that'll give us e to the ln 3 ln y, which is really just y cubed. Okay, you're going to multiply everything by y cubed. So what happens is we're going to get xy to the 4th dx plus 2x squared y to the 3rd plus 3y to the 5th minus 20y to the 3rd, and then dy. Okay, and that equals 0. Okay, so double check again though. Once you get all this done, if you use the right factor, okay, if you use the right factor, then it should be exact. Okay, so it should be exact. So let's check. So the partial of m with respect to y is equal to 4xy cubed. Would that be the same, your partial of n with respect to x? And you can see the y terms with no x's are 0, and it does work out nice where you do get that exactness that we want. And now we could go through the whole process again. So let me just do this last one with you guys because it's good to see more and more examples. So let's start with, our function is going to be the integral of whatever part you pick first, right? So I'm going to pick the first term with respect to x, and here I'll get that 1/2 x squared y to the 4th plus some function of y that we don't know yet. Number 2, what is your derivative of that first part? Okay, with respect to y, so in this case I would get 2x squared y to the 3rd plus the g prime of y. Okay, we are going to set that equal to the part we didn't use yet, so the second term. So I got 2x squared y cubed plus 3y to the 5th minus 20y cubed and solve for g prime of y, which is going to be 3y to the 5th minus 20y cubed. Okay, and now to take the antiderivative of what you got in 3 to find g of y, which is going to be your anti of that derivative with respect to y. So here we get g of y equal to 1/2 y to the 6th minus, so 20 over 4, right? So that's 5 y to the 4th plus now a constant that we need. And now what we could do is substitute that in for g of y. So we get 1/2 x squared y to the 4th plus 1/2 y to the 6th minus 5 y to the 4th plus c equals 0. And there's your final solution. All right, and that's exact equations.